Hello everyone. Let's talk about chi-square test. Okay. Chi-square tests are used with categorical variables. In particular, we have a sample data set, and in this sample data set, we have observations representing different categories of a categorical variable. We count how many times each category is repeated in the sample dataset. So, chi-square tests are used when we have counts for the categories of a categorical variable. There are three types of chi-square tests: goodness of fit test, test of independence, and test of homogeneity. Let's start with goodness of fit test. A goodness of fit test is an inferential procedure. So it makes a conclusion, it makes an inference about a larger population using sample data. And it is used to determine whether the frequency distribution of a categorical variable follows a specific distribution. In other words, is the distribution of counts across all the categories a good fit to a specific distribution? Since it measures goodness of fit to a specific distribution, it is called goodness of fit test. As in all hypothesis testing procedures, we start with defining the hypothesis. The null hypothesis is a statement of indifference. It includes a statement like this: the random variable follows a certain distribution. Okay? And the alternative hypothesis, on the other hand, follows the opposite statement. Okay? The random variable does not follow the distribution in the null hypothesis. So we defined the hypothesis, and let's assume that we have a sample data set, and we would like to test whether the sample data set support the claim in the alternative hypothesis. To test this claim, we start by assuming that the statement in the null hypothesis is true. So the categorical variable follows the specific distribution. Based on this distribution, we calculate the expected value for each category. So expected value for category I, expected count for the ith category, equals the number of observations times the probability in the specific distribution. So out of n observations, how many do you expect for category I is the expected value. OI represents the given observed count in the sample data set for the ith category. Next, we calculate the difference, the difference between the observed value and the expected value. You square this difference, this deviation, and you divide it by the expected value. You do this for all the categories, then you add them up for all the k categories. Okay, and this test statistics is called a chi-square statistics. We represent the chi-square statistics that is computed based on the sample data as chi-square null. Okay, so it is the computed chi-square statistic based on the sample data. This chi-square statistic follows chi-square distribution. Remember that we have k categories, and as t-distribution, the shape of the chi-square distribution depends on the degrees of freedom. So in a goodness of fit test, degrees of freedom equals to the number of categories minus 1. So here we have the chi-square distribution when degrees of freedom is 2. Here we have when degrees of freedom is 5, and so on and so forth. So as you realize, as the degrees of freedom increases, the shape of the chi-square distribution becomes more symmetric. And one thing to notice is chi-square statistics measures the square deviations, hence since square values are positive, non-negative, chi-square distribution takes non-negative values only. And the mean of the chi-square distribution equals to the number of degrees of freedom, and the variance equals to the 2 times the degrees of freedom. So here, the expected chi-square statistic is 2. Here, the expected value of this distribution is 5. The expected value of the chi-square distribution with degrees of freedom 10 is equal to 10. Okay. Now let's go to MyLab and look at the first question. It says that if there is no seasonal effect on human births, we would expect equal numbers of children to be born in each season. So what we expect, equal number of children in each season. So the categorical variable here is seasons, and it has 4 categories: winter, spring, summer, and fall. And we would like to see if we expect equal number of children in each season. To investigate this, a student takes a census of her statistics class and finds that of the 120 students in the class, 26 were born in winter, 35 in spring, 33 in summer, and 26 in fall. She wonders if the excess in the spring is an indication that births are not uniform throughout the year. So we are looking for if the births are uniform across the seasons, or if the births are equally distributed across the seasons. So we immediately recognize that we should apply goodness of fit test because it has counts of data for a categorical variable, and it tests whether this counts of data follows a specific distribution, which is uniform distribution. So if there is no seasonal effect, if the condition of indifference holds, if the null hypothesis is true, about how big on average would you expect the chi-square statistic to be? So the expected chi-square statistic, if you remember, equals to the degrees of freedom, which is the number of categories minus 1. So in this case, it is 4 minus 3. The expected chi-square statistic is 3. Next, the computed chi-square statistics for the given data is 2.2. Does this seem large in comparison to the expected, the mean chi-square statistics value? 2.2 is less than the observed, the computed chi-square statistic is less than the mean. So it does not seem large in comparison to mean in part A. Determine the null and alternative hypothesis. So we should look something along the line, births are uniformly distributed, equally distributed, versus births are not uniformly distributed. So when we look, B seems plausible. Births are distributed uniformly across the seasons. Births are not distributed uniformly across the seasons. What does this comparison in part B say about the null hypothesis? Now, the test statistic 2.2 is smaller than the mean, less than the mean. So remember, the test statistics shows the square deviations of observed values from the expected value. So if we get a small chi-square test statistic, less than the mean, it means that the observed values do not deviate too much from the expected values. So it is possible, it is fair to say the data support the claim in the null hypothesis. In other words, the variable, the categorical variables follow the distribution given in the null hypothesis, right? So let's go here. And since test statistics is small, less than the mean, we can claim the hypothesis in the null hypothesis. And remember, in hypothesis testing, we calculate a test statistic and check whether it supports the claim in null hypothesis. And if it supports the claim in null hypothesis, we fail to reject the null hypothesis, and we support. In this case, we support the null hypothesis, and we do not support the alternative hypothesis, which is the main claim. So we said that there is not sufficient evidence to make the claim in the alternative hypothesis. As you see, the births are not distributed uniformly across the seasons is the alternative hypothesis. So we do not, since we support the data support the null hypothesis, we say that there is not sufficient evidence, there is little evidence, not sufficient evidence that the births are not distributed uniformly across the seasons. Okay.